Types of solutions and solubility. So here's a table showing types of common solutions. So you can have a solution of two gases. This one's really common. We call it air. So this room full of a solution. Mainly oxygen and nitrogen gases, also with some argon and water and various other things. We can have solutions where the solvent is a liquid. We can have a gas dissolved in a liquid dissolved in a liquid, or a solid dissolved in a liquid. So club soda, the bubbles are carbon dioxide dissolved in water. Vodka is ethanol in water. Seawater is salt in water. You can also have solid solutions, solids dissolved in each other. Alloys are solutions of metals. So brass. Brass is a mixture of copper and zinc. Pewter is a mixture of metals. Stainless steel is a mixture of metals. They are solutions because they are homogeneous and they are mixtures. Yes?
Why doesn't vodka freeze?
Why doesn't vodka freeze? That's an excellent random question.
Wait, won't it freeze like that? Really?
It would freeze at a low enough temperature. We will actually kind of get to that. It has a little to do with the ice cream that we made. The freezing point depression. So when you stick something in water, any type of a thing that will dissolve, it will lower the freezing point. But then you also have an additional thing going on there, that the freezing point of pure ethanol is lower than that of water. It will freeze eventually, but probably not in your home freezer. I like that question. So when we talk about an aqueous solution, which we've used this word a lot, we mean that water is the solvent. The solute could be anything, gas, liquid, solid. But aqueous means the water is the solvent. And that's most of the time we're talking about aqueous solutions. The word solubility refers to the amount of substance that will dissolve. Okay, there's a typo on that. That's not right. In a given amount of solvent. It's really disturbing to me that this is my third time through these slides and I'm still finding mistakes. Solvent. It's the amount of substance, solute, that will dissolve in a given amount of solvent. So that's what we mean by solubility. Nature's tendency toward mixing has a name. It's called entropy. As we've learned, a lot of physical systems tend toward lower potential energy. That is a driving force of a lot of things that happen. Why does a ball roll down the hill? Because it's going to a lower potential energy. When we make a solution, it doesn't necessarily lower the potential energy of the constituent particles. So we can't think of the mixing of two ideal gases as lowering their potential energy. Here you have a sample of neon gas and argon gas that are separated by a divider. When you remove that divider, they mix. Does that have anything to do with their potential energy? Not really. That's a good switch from the shaking, nodding to the shaking. Entropy is energy randomization or energy dispersal, things spreading out, an increase in disorder. So when you have two ideal gases mixing, the kinetic energy of each gas gets spread out or dispersed through a larger volume. The entropy has increased. It's not the potential energy, but it's the entropy increasing. And that's why substances mix, this pervasive tendency for energy to spread out whenever it's not restrained. This also explains why thermal energy flows from hot objects to cold ones, because the thermal energy wants to spread out. Everything just wants to spread out and mix uniformly, and that's the natural tendency You can, we didn't mean to do this experiment with the Legos, but we inadvertently did. We spent most of spring break one year sorting Legos into big boxes of different colors and types, and so that we could actually recreate all of the Lego things that we owned. It didn't go very well, but we did get a lot of sorting done. Are those Legos still sorted? No. Entropy took over. They're pretty uniformly mixed up now. It took a while, but they just get all mixed up together again. And molecules do that as well. Energy does that as well. It spreads out. Intermolecular forces have an effect on the formation of solutions. They can promote the formation, or they can prevent it. So these are the types of intermolecular forces. Again, we've got the dispersion forces, and those occur between all molecules, but they're the only force and the most significant force for nonpolar molecules. Dipole-dipole forces are between polar molecules. Hydrogen bonds are between particular polar molecules. Remember, ET, phone home. And these are stronger. And then we have the ion dipole forces, where we have an ion interacting with a permanent dipole. It's the relative strength of the interactions between the solvent molecules and the solute molecules that determines whether too many sol words, whether a solution will form. So in this example, we can have interaction between the solvent molecules, we can have interactions between the solute molecules, and we can have interactions between solvent and solute molecules. So if the solvent-solvent interactions are similar to the solute-solute interactions, then a solution will form. And so we have an expression, like dissolves like. If these are alike in their intermolecular forces, they will probably dissolve in each other. If we have very weak solvent-solute interactions compared to the interactions of each of the components with themselves, then the gain in entropy isn't going to make up for the energy lost by giving up these interactions, and so the solution will not form. So we have, in a solution that does form, you're losing your solvent-solvent interactions and some of your solute-solute interactions, and you're gaining solvent-solute interactions. That's a very appropriate look you're giving me. You're like, this is, yeah, I know it is. But we're going to go here anyway. If these interactions are similar in strength or stronger, then everything's good. If these are really weak, it's not worth giving up those interactions to make these, even though you do get some entropy from spreading out. And so the solution will not form, and the solute molecules will stay to themselves, and the solvent molecules will stay to themselves. So an example, determine whether each compound is soluble in hexane. And we're doing this just based on types of intermolecular forces. So hexane is C6H8. What is the strongest intermolecular force that molecule probably has? Does it look like it would be a polar molecule? Yeah, this is going to have dispersion forces. Carbon-hydrogen bonds are considered nonpolar bonds. And all we've got is carbons and hydrogen. That's going to be a nonpolar molecule. What kind of intermolecular forces? Let me rephrase that. They all have dispersion forces. So we're going to talk about the strongest one. What's the strongest intermolecular force that water has? Hydrogen bonding. So So we've got hydrogen bonding for water and dispersion forces for the hexane. Are they going to dissolve? No. They're two different. What kind of forces does ammonia have? The strongest one. Okay, I know you're not being shy, because hydrogen bonding, thank you. So, is ammonia going to dissolve in hexane? No. Propane. CH3, CH2, CH3. What kind of forces? Is it polar? No.
Dispersion.
Nonpolar, all it's got is dispersion forces. So its strongest force is dispersion forces. Hexane's strongest force is dispersion forces. Are these going to dissolve? Yes. How about hydrogen chloride? What kind of... Does that have hydrogen bonding? No. E.T. phone home. I don't see F, O, or N in there. That's what it stands for. I couldn't figure out why she kept talking about ET. In order to have hydrogen bonding, we have to have fluorine, oxygen, or nitrogen bonded to hydrogen. Here we have hydrogen. This is a polar molecule, no hydrogen bonding. So what kind of forces does it have? Dipole, dipole. Dipole, dipole forces. Those are rusty. So dipole, dipole forces, the strongest one, those are stronger than dispersion forces. Is hydrogen chloride going to dissolve in hexane? No. So a question like this, the idea is, do the two things you're looking at have the same strongest intermolecular force? If yes, we predict that they will dissolve, form a solution. If they're not the same, we predict that they will not. Okay?